Hello everyone, myself Kirti. I am a student of BSc Chemistry Honours final year. This is an audio recorded lecture of the topic Metal-Ligand bonding in transition metal complexes. Transition metals have very good tendency to form coordination compounds or complexes. Though many attempts were made by different workers to explain the bonding and structure of coordination compounds, the main credit goes to the brilliant work of Werner. In 1893, Werner proposed a theory which is commonly known as Werner coordination theory. This was the first successful attempt to explain the bonding in coordination complexes. In recognition of his work in his field, Werner was awarded Nobel Prize in 1913. He explained the bonding in these complexes on the basis of two types of valencies of the metal, the primary valency corresponding to oxidation state and the secondary valency corresponding to the coordination number. The secondary valency or coordination number determined the stereochemistry of the complexes. However, the Werner's assumptions were not based on theoretical justification, and the scientists started making attempts to find basis of bonding in these complexes. The first attempt in this regard was made by Sidgwick, who extended the Lewis theory of electron pair bond formation to explain the bonding in transition metal complexes. He suggested that metal ion or atom accepts electron pair from ligands until it achieves the next noble gas configuration and give a term effective atomic number. Effective atomic number is the total number of electrons possessed by the central metal ion and the electrons gained by its from ligand. However, this theory lacked fundamental basis and simply gave emphasis on the stability of inert gas configuration in coordination compounds. With the advances in theories of chemical bonding, three modern theories of bonding in transition metal complexes have been developed. These are valence bond theory, crystal field theory, and molecular orbital theory. In the present text, we shall discuss mainly crystal field theory of bonding. The valence bond theory has already discussed in the previous classes. Valence bond theory. The valence bond theory was developed by Linus Pauling and assumes the bonding between the metal atom or ion and the ligand to be purely covalent. It presents a simple description of metal-ligand bonding using hybrid orbitals of the metal and the electron pair of the ligands. The basis of valence bond theory is that the appropriate vacant atomic orbital of the metal atom hybridized to give a set of hybrid orbitals which are directed towards the ligands according to definite geometry of the complex. The bonding in metal complexes arises when a filled orbital of the ligand containing a pair of electrons overlap with a vacant hybrid orbital on the metal atom or ion, forming a covalent sigma bond called coordinate bond. This is the diagram which shows that how a coordination covalent bond forms. In addition to a sigma bond, there is also a possibility of pi bond provided suitable orbitals are available on the metal atoms and the ligands. The total number of metal atomic orbitals undergo hybridization is equal to the coordination number of the central metal atom or ion. For example, for coordination number 6 complexes, 2d, 1s and 3p orbitals, that is, a total of 6 orbitals of the metal atom are involved in hybridization. The d orbitals involved in the hybridization may be either inner n-1d orbital or outer nd orbitals, giving inner orbital or outer orbital complexes. For example, in case of octahedral hybridization, the orbitals may be 1ns, 3np and 2nd or 1ns, 3np and 2n-1d hybridization. Similarly, for coordination number 4 complexes, tetrahedral structure can be considered to arise from bonding with 4 sp3 hybrid orbitals formed by the combination of 1ns and 3np atomic orbitals, or square planar structure arising from bonding with 4 dsp2 hybrid orbitals using n-1d, ns and 2np atomic orbitals. This is the table which shows the correlation of hybridization with coordination number and geometry of complexes. Coordination number 2 has a hybridization sp and its shape is linear. Coordination number 3 has a hybridization of sp2 with trigonal planar shape. Coordination number 4 has a hybridization of sp3 with tetrahedral shape. Coordination number 4 has a dsp2 hybridization with square planar shape. Coordination number 5 has dsp3 hybridization with trigonal bipyramidal shape. Coordination number 5 has sp3d hybridization with square pyramidal shape, and coordination number 6 complexes have d2sp3 or sp3d2 hybridization with octahedral shape. Limitations of valence bond theory. The valence bond theory successfully explained many stereochemical and magnetic properties of coordination compounds. However, it has many limitations. The main limitations of the VBT are: first is it provide only qualitative explanation for complexes. Second is it does not explain the color and electronic spectra of complexes. Third is the theory fails to explain why some metal complexes in a particular oxidation state are low spin complexes, while some other complexes of the same metal ion in the same oxidation state are high spin complexes. For example, in the complexes CONH3 6 3 positive and COF6 3 negative, the oxidation state of cobalt is +3, but the former is low spin complex and the latter is high spin complex. Fourth limitation is it does not predict the relative stability of different complexes. We know that certain complexes are liable, in which the displacement of ligand take place rapidly, while some are inert, in which ligand displacement by another ligand is very slow. Valence bond theory does not explain the kinetic inertness of complexes such as Cr3 and low spin CO3 octahedral complexes. Fifth limitation is it does not explain the variation of magnetic moment values with temperature. Next is it does not take into account the splitting of d energy level. Next is it does not predict the relative stability of different structure. Next is the valence bond theory does not predict whether the four coordinate complexes will be square planar or tetrahedral. This can be explained only on the basis of magnetic moment value of the complex. For example, the decision about the geometry of nickel second complexes depends upon the magnetic moment values. For example, nickel second ion has the electronic configuration 3d8. If the complex involved sp3 hybridization, it would have tetrahedral structure. For the formation of tetrahedral structure, the 3d orbitals remain unaffected and the complex is paramagnetic. On the other hand, if the complex involves dsp2 hybridization, it would have square planar structure. This is possible if the two unpaired d electrons are paired up, thereby making one of the 3d orbital empty. There is thus no unpaired electron and the complex would be diamagnetic. It also fails to give a satisfactory explanation for the formation of square planar tetraamine copper second ion. Ninth limitation is the valence bond theory does not tell us why water and halide ions commonly form high spin complexes while cyanide ion form low spin complexes. To answer some of the above limitations, let us discuss some other theories. Crystal field theory. The crystal field theory was developed by H. Bath and V. Black. This theory is based on entirely different assumptions than the VBT. As we have already learnt, the VBT considers the bonding between the metal ion and ligands as purely covalent. On the other hand, the crystal field theory considers the bond between metal ion and the ligand as purely electrostatic. This theory is based on the assumptions that the metal ion and the ligand act as point charges and the interaction between them are purely electrostatic. In case of negative ligands, anions such as chlorine, chloride, bromide, cyanide, the interaction with metal ion are ion-ion interaction. If the ligand are neutral molecule such as NH3, H2O, CO, the interaction with the metal ion are ion dipole interaction. For example, in the case of complex ion COF6 3, the interaction are CO3 positive and F negative ion, whereas In CONH363 positive, the interaction are between negatively charged end of NH3 molecule and CO3 positive ion. The central idea of this theory is that the electrons of the metal ion in the environment of other ion or molecule, as for example within the lattice of a crystal, are affected by the non-spherical electric field established by the surrounding ions or molecules. The electric field was called the crystalline field, but now it is called as crystal field. This is responsible for the name crystal field theory. Basis of crystal field theory are: first, the transition metal ion is surrounded by the ligand with lone pair of electron. Next is all types of ligand are regarded as point charges. The ligands may be either ionic or molecules. If the ligands is a neutral molecule, then the negative end of the dipole is oriented towards the metal ion. For example, ammonia is polar molecule having delta negative charge on N and delta positive charge on H atom. Similarly, water is also polar with del charge on O and del positive charge on H atom. Third assumption is the interaction between the metal ion and the negative ends of the anion is purely electrostatic. That is, the bond between the metal and ligand is considered 100% ionic. Fourth assumption is the ligand surrounding the metal ion produce electrical field and the electrical field influences the energies of the orbital of central metal ion, particularly d orbitals. Fifth is, in case of free metal ion, all the 5 d orbitals have the same energy. These orbitals having the same energy are called degenerated orbitals. This means that an electron can occupy any one of these 5 orbitals with equal ease. However, on the approach of the ligands, the orbital electrons will be repelled by the lone pairs of the ligands. The repulsion will raise the energy of the d orbitals. If all the ligands approaching the central metal ion are at equal distance from each of the d orbitals, the energy of each orbital will increase by the same amount. Therefore, these orbitals will still remain degenerate, but they will have higher energy than before. But we know that d orbitals have different orientations, and therefore these orbitals will experience different interaction from the ligands. The orbital lying in the direction of the ligands will experience greater repulsion and their energies will be raised to greater extent. On the other hand, the orbitals lying away from the approach of the ligands will have lesser interaction and therefore their energies will be raised to lesser extent. Therefore, due to electrical field of the ligands, the energies of the 5d orbitals will split up. The conversion of a 5 degenerate d orbital of the metal ion into different sets of orbital having different energies in the presence of electrical field of ligand is called crystal field splitting. This concept forms the basis of crystal field theory. Sixth assumption of crystal field theory is that the number of ligands and their arrangement around the central metal ion will have different effect on the relative energies of the 5d orbitals. In other words, the crystal field splitting will be different in different structures with different coordination numbers. Next assumption is that the magnetic properties, spectra, and preference for particular geometry can be explained in terms of splitting of d orbital in different crystal fields. Thus, to understand the crystal field theory, it is essential to have a clear picture of the disposition of the 5d orbitals in space and the geometrical arrangement of the ligands around the central metal ion. We may illustrate that concept by considering the complexes with coordination number 6 and 4, which are very common. Shapes of d orbitals. There are 5d orbitals. These are designed as dxy, dyz, dzx, dx square minus y square, and dz square. The shapes of these orbitals are described. First, the three orbitals dxy, dyz, and dzx are similar and each consists of 4 lobes of high electron density lying in xy, yz, and zx planes respectively. These lobes lie in between the principal axes. For example, in case of dxy orbitals, The four lobes lie in xy plane in between the x and y axis. The dx square y square orbital has also four lobes of high electron density along the principal axis x and y. It may be noted that this orbital is exactly like dxy orbital except that it is rotated through 45 degree around the z axis. The dz square orbital consists of two lobes along z axis with a ring of high electron density in the xy plane. These are the shapes of the 5d orbitals. It may be noted that although dz square and dx square minus y square orbitals do not look to be similar, yet they are equivalent so far as interaction with the metal ion are concerned. The dx square or the dz square orbital can be regarded as a linear combination of two orbitals, dz square minus x square and dz square minus y square, each of which is equivalent to the dx square minus y square orbital as shown below. However, it may be noted that these two orbitals, that is dz square minus x square and dx square minus y square, do not have independent existence, but the dz square orbital can be thought of as having the average property of the two. Since both the orbitals dz square minus x square and dz square minus y square have high electron density along the z-axis, therefore dz square orbital has a large fraction of electron density concentrated along z-axis. Moreover, one of the component orbital dz square minus x square has lobes along the x-axis also, and the other dz square minus y square has lobes along the y-axis. The resultant d orbital has electron density in xy plane as shown as donut, ring or a collar. Next topic is crystal field splitting in octahedral complexes. In an octahedral complex with coordination number 6, the metal ion is at the center of the octahedron and the ligands are at 6 corners. The three axes x, y and z point along the corner of the octahedron. Let us suppose that the metal ion, that is Mn positive, has a single d electron, d1 that is d1 configuration, example type Ti3 positive in TiF63 negative complex. In the free ion, when there is no ligand, the electron can occupy any one of the 5d orbital because all are of same energy and are called degenerate orbitals. However, in the octahedral complexes mx6, all the 5d orbital will not remain of equal energy. This can be easily understood by considering the shapes of these orbitals in the octahedral field of ligands. The comparison of arrangement of d orbital shows that the two lobes were of that the two lobes of dz square orbitals and four lobes of dx square minus y square orbital point directly towards the corner of the octahedron where the negative charge of the ligands are concentrated. The remaining three orbitals are oriented in between the axes. In the case of octahedral complexes, the former two orbitals are designed as Eg orbitals while the later three orbitals are designed as T2G orbitals. As the two ligands approach the central ion along the axis, the Eg orbitals are repelled more than the T2G orbitals. In other words, the energy of dz square and dx square minus y square orbital increases much more than the energy of the dxy, dyz and dzx orbital. The greater the repulsion, the greater is the increase in the energy. Thus, in octahedral complexes, the 5d orbital split up in two sets. One set consisting of two orbitals of higher energy, that is Eg orbitals, and the other set consisting of three orbitals of lower energy, that is T2G orbitals. The phenomena of crystal field splitting in an octahedral complex is illustrated below. This is shown crystal field splitting in an octahedral complex. The energy difference between two sets of d orbitals T2g and Eg is called crystal field splitting energy and is symbolically represented as del O. The magnitude of del O varies for different complexes. The crystal field splitting is also measured in terms of another parameter called dq. The two are related as del O is equal to 10 dq. These two parameters are very commonly used. Next topic is crystal field stabilization energy, CFSE. We have learned that in an octahedral field the energies of 5d orbitals split up. 3 orbitals are lowered in energy and 2 orbitals are raised in energy. We know that electrons always prefer to occupy an orbital of lower energy. For example, in case of d1 system, the d electron will prefer to occupy a T2g orbital and is therefore stabilized by an amount equal to 0.4 del O or 4 dq. The amount of stabilization provided by splitting of the d orbital into two levels is called crystal field stabilization energy. It is abbreviated as CFSE. Thus, in octahedral field, for each electron entering into the T2g orbital, the crystal field split stabilization is minus 4 dq, and for each electron entering into the Eg orbital, the crystal field splitting entering into the Eg orbital, the crystal field destabilization energy is plus 6 dq. Thus, the CFSE is calculated as the algebraic sum of minus 4 dq per electron in T2g level and plus 6 dq for each electron in Eg orbital. Next is CFSE for various octahedral complexes. First, for D1 system, electron will be present in any one of 3 T2g orbitals. The electronic configuration may be written as T2g1. The crystal field stabilization energy is minus 4 dq. Next, for D2 system, the electrons will occupy T2g orbital with their spins parallel in accordance with Hund's rule. The electronic configuration is T2g2 and crystal field splitting and crystal field stabilization energy is minus 8 dq. Third is, similarly for a D3 system, the CFSE is minus 12q. For a D4 system, there are two possibilities. First is, all the 4 electrons may occupy T2g orbital with 1 electron gets paired. The electronic configuration may be written as T2g4. And second possibility is that the 3 electrons occupy T2g orbital and the 4th electron goes to one of the Eg orbital, and then the configuration will be T2g3 Eg1. The actual configuration may be decided on the basis of del O and the pairing energy P, that is the energy required to pair the electron with one another. The configuration A is possible if del O is greater than pairing energy. These complexes are called strong field complexes because del O is large. In this case, the complex has less number of unpaired electrons and is called a low spin complex. The configuration B is possible if del O is less than pairing energy. It is called weak field and the complexes are weak field ligands. In that case, the maximum number of electrons remain unpaired and the complex is called high spin complex. Thus, we may generalize that if del O is greater than P, then the ligand is a strong field and the complex is a low spin, and if del O is less than pairing energy, then the ligand is weak field and the complex is high spin. As shown above, for a low spin complex having T2G4 configuration, CFSE is minus 16 dq. However, if we take into account pairing energy, the net CFSE become minus 16 dq plus P. On the other hand, for a high spin complex having the configuration T2G3 Eg1 CFSE will be minus 6 dq. Next, for D5 system, there are two possibilities as well. A. All the 5 electrons may occupy T2G orbital with the 2 orbital gets paired. The electronic configuration may be written as T2G5. This is possible if del O is greater than P and the complex will be called strong field or low spin complex. Next possibility is that the 3 electron occupy T2G orbital and 2 electron occupy Eg orbital. The electronic configuration may be written as T2G3 Eg2. This will be possible if del O is less than P and the complex is called weak field or high spin complex. The CFSE in these two types of complexes will be strong filled if del O is greater than P, that is CFSE will be minus 20 dq plus 2p, and the CFSE in weak filled ligand is 0 if del O is less than P. Similarly, D6 and D7 system have two possibilities depending upon the relative magnitude of crystal field splitting energy and the pairing energy of the electrons. For a D6 system, example CO3 positive, for strong field del O is greater than P and CFSE will be minus 24 dq plus 2p. For weak field del O is less than P and CFSE will be minus 4 dq. For a D7 system, example CO2 positive ion, in strong field del O is greater than P and CFSE will be equal to minus 18 dq plus P. For weak field del O is less than P and CFSE will be equal to minus 8 dq. The D8, D9 and D10 system have only one possible configuration. This is because if we assume the complex to be high spin, the first 5 electron would go 1 each into the 5d orbital and remaining 3, 4 or 5 electron would fill the T2G and Eg orbitals. But if we assume the complex to be low spin, the first 6 electrons would fill the T2G orbital and the remaining 2, 3 or 4 electrons would go into the T2G orbitals. In both cases, the configuration will be the same. Therefore, there is only one possible electronic configuration for D8, D9 and D10 system. For a D8 system, example Ni2 positive ion, CFSE will be minus 12 dq. For a D9 system configuration, example Cu2 positive, CFSE will be equal to minus 6 dq. For a D10 system, example Zn2 positive ion, CFSE will be 0. The d electron configuration for weak field and strong field of octahedral symmetry are given in the above figures. The crystal field stabilization energy for metal ions having different configuration are summed up in the table given. It may be noted that for strong field, the electron always pair up in the lower level first, that is T2G, filling it before entering the higher level Eg. For weak field, each orbital, whether of high Eg or low T2G energy, receive one electron each before any pairing starts. Therefore, weak field configuration always have the same pairing scheme as the free ions. This is the splitting shown for different configurations for D1, D2, D3, D4, D5, D6 up to D10. This is another table which show crystal field stabilization energy for metal ions having different number of d electron in octahedral complexes. This is the summarized table. Next topic is crystal field splitting in tetrahedral complexes. The coordination number for tetrahedral complexes is 4. The tetrahedral arrangement of 4 ligands surrounding a metal ion may be visualized by placing ligands on the 4 of the 8 corners. Ligands surrounding a metal ion may be visualized by placing ligands on the 4 of the 8 corners of the cube. The direction x, y and z point to the center of the faces of the cube. From the figure given below, it is clear that the orbital dxy, dyz and dzx point between the xy and z axis, that is towards the center of the edges. Whereas the orbitals dx square minus y square and dz square points along x, y and z axis, that is to the centers of the faces. It is clear that in tetrahedral field none of the d orbital point exactly towards the ligand, and therefore the splitting of energy will be less than that in octahedral field. The 3d orbitals, that is dxy, dyz and dzx, are pointing close to the direction in which the ligands are approaching, while the two orbitals dx square minus y square and dz square are lying in between the ligands. Therefore, the energies of the 3 orbital will be raised while the energy of the 2 orbitals will be lowered. Thus, in the presence of tetrahedral field, the degeneracy of 5d orbital splits up as: first, the two orbitals dx square minus y square and dz square become stable and their energies are lowered. These are designated as e orbitals. Second, the three orbitals dxy, dyz and dzx become unstable and their energies are raised. These are designated as t2 orbitals. This is diagrammatically shown below that how splitting in tetrahedral field occurs. The magnitude of crystal field splitting is the difference between E and T2 orbital and is designated as del T. It is also measured in terms of dq, and del T is equal to 10 dq. If we compare the magnitude of crystal field splitting in octahedral and tetrahedral complexes, it has been observed that the crystal field splitting in tetrahedral complex is considerably less than in octahedral complexes. It has been found to be del T is equal to 4 by 9 del O. Reason for the smaller value of crystal field splitting in tetrahedral than in octahedral complexes. There are two main reasons for this. First is, in tetrahedral complexes there are 4 ligands while there are 6 ligands in octahedral complexes. Therefore, lesser ligand produce less crystal field splitting. The crystal field splitting in tetrahedral field is about 2/3 of the octahedral field. Second is, in tetrahedral field none of the orbital is pointing directly towards the ligands and therefore splitting is less. Since the magnitude of the crystal field splitting in tetrahedral field is quite small and is always less than the pairing energy, therefore the pairing of electron will never be energetically favorable. Thus, all the tetrahedral complexes are high spin complexes. No tetrahedral complex with low spin has been found to exist. It is interesting to note that the splitting pattern is inverted when octahedral is replaced by tetrahedral symmetry. This is the diagram which show comparison of octahedral and tetrahedral field of ligands. Next topic is crystal field stabilization energy for tetrahedral complexes. As we know that an electron always prefers to occupy an orbital of low energy, since average energy of the d orbital does not change. Therefore, in terms of 10 dq, the energy of each of the e orbital is lowered by 6 dq, and the energy of each of the t2 orbital is raised by 4 dq. CFSE is therefore calculated as algebraic sum of minus 6 dq per electron in e orbital and plus 4 dq for each electron in t2 orbital. In terms of del T, the energy of each e orbital is lowered by 3 by 5 del T, while each of the t2 orbital is raised by 2 by 5 del T. For example, for D1 system, CFSE is minus 6 dq. For D2 system, CFSE is minus 12 dq. For D3 system, CFSE is minus 8 dq. The CFSE4 complexes with metal ion having different configuration of d orbital in tetra field are given in the table. For D4, CFSE is minus 4 dq. For D5, CFSE will be 0. For D6, CFSE will be minus 6 dq. For D7, CFSE will be minus 12 dq. For D8, CFSE will be minus 8 dq. For D9, CFSE will be minus 4 dq. And for D10, CFSE will be 0. So this is all for today's video. Thank you all.